In this webinar, I will be dealing with methodology for statistical analysis when we are confronted with small trials, which is of course very common in rare diseases. And not only trials, it can also be observational studies, it can be life history data, real world data. It can be about everything, but at the same time, when we deal with a lot of data, so large studies. And interestingly enough, in rare diseases, they can occur simultaneously. Think, for example, of a study, let it be a clinical trial or a registry, with a small to moderate number of subjects, patients, participants on the one hand, but about whom a lot of data is collected. Longitudinally over time, many measurements are taken. You may also think of, for example, wearable devices that produce a lot of data, but still the sample size may be relatively small. In that sense, we would like to often apply statistical methodology, which is common in other areas as well, to find, is there a treatment effect? Is there an evolution over time? Do we see subgroup differences, etc.? But taking these, let's say, peculiarities, limitations of our studies into account. And to get us started, I would like to discuss the epilepsy study, which is a classical clinical trial, 45 placebo patients, which basically means people who get standard treatment, and then patients in the active arm who on top of that get a new anti-epileptic drug. So roughly 90 patients that are followed after a run-in period for 60 weeks into the primary follow-up. Some go beyond that until week 27, but we will not spend too much time on that. The outcome is number of epileptic seizures, a count, can take values 0, 1, 2, 3, etc., measured during or counted during the period of a week. And of course, what we would like to see is that there is a reduction in seizures in the sense that the evolution over time is more favorable in the active arm than in the placebo arm. What I will do first is point to a number of features behind this seemingly relatively simple trial that we need to take into account. But before we do that, here is a view on the actual data. At the top, you see the placebo arm and the active arm. And what is obvious is that several profiles in both groups, quite many, follow more or less the trend that we see overall. But many also jump up and down all the time, meaning that there is a subgroup of patients that has, for a certain period of time, a large number of epileptic seizures over a 1 week period, whereas at other times it's actually relatively low, 0 or near 0. That's also reflected in the average number of seizures that we count per subject. So the bottom two profiles or two graphs are just the ID number of the patient on the x-axis, and then for that patient over the period of observation, how many measurements we have available. Is that 16 weeks for all? No, well, some people actually stop the trial a little earlier, so the number of measurements is actually variable from one subject to the next. Okay, we will not get too technical, but let's just say what would we take in terms of modeling approach typically. It's a count. The count is measured repeatedly over time. So returning to the fact that it's a count, we would then use a Poisson model very often. And the fact that we have repeated measures over time implies that there is potentially correlation between the number of seizures of a given subject in 1 week and the following week, for example. That needs to be taken into account. So for that, we often use models that include random effects. Okay, what I would like to do now is point you one step at a time to issues that occur, features in the data, as it were, that also need to be taken into account. But for now, we have a Poisson model, the basic model, as it were, for counts, and we have normal random effects. But these random effects, they account for two things at the same time. As we said, correlation between repeated measures of the same subject. Fair enough. but also over dispersion. Because the thing is with the Poisson model, a technical feature of the Poisson model is that the mean and the variance are equal. Nice, only the data, the patients, the clinicians don't always know that. So the data are what they are, and yes, often the variability is much larger than what is predicted by the Poisson model, meaning that this basic model is actually chronically insufficient. We need to extend it a little bit. So for that, without giving too many details, we often include a second random effect. And what it comes down to is, let's say if there is moderate correlation, okay, the normal random effect will take that moderate correlation into account. Check. It will, as a consequence, also take moderate over-dispersion into account. But what if there is not moderate, but a lot of over-dispersion? Well, then the second random effect will allow us to expand it to that level. In other words, we give the model more freedom to describe the data as it is. The count, which is the mean profile, the variability in that count between subjects, within subjects, with as consequences correlation and over-dispersion. All of these features are taken into account. So the model that we would consider in a case like this is predominantly we're interested in, of course, the evolution over time in the placebo and the treated group, and also how these two parameters, beta 01, beta 11, so the evolution over time in the placebo group, in the treated group, how they relate to each other. Null hypothesis, they're identical. The alternative would be they're not identical, and then we hope that it's more favorable in the treated than in the placebo group. We complete a model by intercepts, which is basically the starting point, the number of seizures in the placebo group on the one hand, and for a particular patient, patient number I in the placebo group on the other hand, and likewise in the active group. The index I just said it, stands for the patient, and that would be from 1 to 89 in this case. J is the measurement occasion within a patient, and if we focus on the first 16 measures, that would go from 1 to 16 indeed. By the way, we cannot be sure, and it's actually the case, not all subjects, and I already said that, make it until the end of the study. They may miss a visit, but they may also drop out. Fortunately, the way we will approach our modeling exercise will be broadly valid when data are incomplete. I will not spend too much time on incomplete data as such, but it's of course an interesting topic and an important topic on its own. So, we have already several options by constructing a base model and then add some features to it, buy some additional pieces to stick onto the Poisson model. So the Poisson model I would not spend too much time on. I will say in a moment why, because it's assuming that the mean and the variance are equal, doubtful, and it's assuming that there is no correlation between repeated measures, extremely doubtful. The negative binomial does allow for some over-dispersion, but still not for correlation. The Poisson model, that's already a bit better because it allows for correlation and over-dispersion, but in our case, both should be then strong or both should be weak, and that may not be the case. The combined model, remember, with its normal and its additional random effect, allows for freedom. The correlation can be small, moderate, say, and the over-dispersion can be strong, and yet the model can still capture that. So if we now see what this implies for the correlation function, let's do that first, and then look at the hypothesis testing. It's clear that the Poisson normal model produces correlations, whether in the placebo or in the active group, somewhere in the range from 0.85 to 0.90, and we would be inclined to conclude that there is a strong correlation. But the combined model drastically improves the fit of the model, and it says, wait a minute, the correlation is weaker. It's somewhere between 0.20 and 0.30. Why? Once again, the correlation is weak, but because there is strong over-dispersion, the Poisson normal model has no other chance but to assume that and to basically predict, describe that both are large, contrary to fact. Okay, It's interesting to say that our model is more general, but what does it mean for actually hypothesis testing? Well, we have these two slopes. They basically describe the evolution of the number of epileptic seizures per week over time. And the null hypothesis is there's no difference between the two, which means either their difference is zero, that's saying the same thing. Another way to say the same thing is their ratio is equal to 1. From hypothesis testing perspective, that's not necessarily exactly the same thing. One may have a bit more power than the other, but look at that. The Poisson model says no matter how you look at the problem, there is a significant treatment effect. The Poisson normal model said, I don't know. If you look at the difference between the slopes, we don't find anything, and with the ratio, yeah, there is some marginal evidence. The negative binomial, which doesn't allow for correlation, has the differences significant, but the truth of the matter is, and of course we may not like that, if we are interested in the treatment effect, of course, and we have vested interest, maybe even commercial interest or clinical interest in the treatment effect, the combined model says, well, if you model the data carefully, nothing is happening. Is that the end of the story? No, no. There are a few other features that we still should think about, and the first is, aren't there influential subjects? Is the conclusion genuine, or may it be driven by one or a few subjects that have an undue effect on the conclusions? And we are thinking, of course, spontaneously, of course, not just spontaneously, they're also printed here. The profiles that dance up and down, the oscillators, so to speak. And that may be people who have a relatively large number of epileptic seizures, relatively mild. So because of the circadian rhythm, if that happens during daytime, you will record it. If that happens during nighttime, many of them, if not all, may go unnoticed. And of course, that huge variation between not just measurements, but these subjects and the rest of the data may skew the conclusions a little bit. So what happens if we remove these guys? The treatment effect, which was not significant before, becomes now just marginally significant. Are we saying, hooray, we finally found the treatment effect, we close the books? No, but it just, no, that's a bit too quick, but it just shows that these oscillators in general, that influential subjects may have a fairly strong impact on the conclusions. Good, so over and above what we had available already, we now added what we call influence analysis. You can call it outliers or minority profiles, etc., which is something that we find in many clinical areas. There is something else, though, that I would like to discuss. And then there is something else after that. But for now is, we have actually tested for the treatment effect. Fair enough. But what if I want to estimate the treatment effect? Well, the models that we are considering are random effects models. This means that the interpretation of the parameters has to be done with great caution. If you look, for example, at the difference between the two betas, in a random effects model, it's the difference between two typical patients, one placebo, one active, with the same level of the random effect. You might say with the same, more or less, average number of epileptic seizures at the beginning of the study, or in the run-in period, if you wish. Yeah, that may be interesting, but we, regulators, we might want to know what is the treatment effect overall when I compare the placebo group as a whole to the active group as a whole. So there are a number of ways, and I will not provide you with details right now. They can be found in the literature also, and a list of references is coming soon. But there are ways to extract the marginal interpretation from the model we have here. So brief, in summary on this particular topic, the random effects model, they look at the treatment difference of people at the same level of the random effects. And if you say, yeah, but what exactly does that mean, having the same level of random effect? I gave an interpretation, but the very fact that we have to ask ourselves that question says, it's not a natural clinical trial question. That is, what is the difference between a group of patients getting placebo and a group of people getting active treatment? So we just stack it on. We buy more supplies or more devices to put on our machine, and that is now a proper marginal interpretation. We have actually 6 models here. The original models without over-dispersion, but then with marginal interpretation, and the models with over-dispersion. Well, actually, I would like to focus on the models with over-dispersion. They're already better. And what we see here is that 2 of the ways of marginalization are identical. The other way, if you look at the slope here and the slope there, is also providing something that is not different. So brief marginalization comes up in this case with a very clear, unambiguous solution. The slope parameters for the placebo and the treatment group are the same, and so are the standard errors. The one difference is in the standard errors and actually the estimates of the intercepts, but we're not so much interested in those. So it is actually more fair to compare the marginal treatment effects in this way. There's yet something else that I would like to bring on the table. And it's a phenomenon that occurs whenever we have counts or correction, in many cases where we have counts, not just in clinical and biopharmaceutical research, but also, for example, in traffic safety. If you take an intersection, which is known as a pretty dangerous intersection with many road accidents, car accidents, you can count the number of car accidents in a day, pretty much like you do with epileptic seizures. But there may be days with 0, and then another one with 0, and another one with 0, and then it's, I see, 7 accidents. So there are more zeros than the model actually predicts. The Poisson model, you know, it has a lot of a prioris, mean is equal to variance, but we had to relax that. A certain number of zeros, which is in line with the number of ones and the number of twos, but we have to relax that with the so-called zero inflation or hurdle models. And yeah, we can do that now, and then we extend our toolkit. And we conclude at the end of the day that we've actually built in our model quite a few different features. We have counts, check, that's taken into account. The counts are measured repeatedly, which means there is correlation of 2 or more counts of the same subject taken into account, check. The variability may be much larger than what the Poisson model predicts, but we have taken that into account. And then we examined, are there outlying subjects, yes or no, that should get special treatment and maybe taken out of the primary analysis and studied separately. We've done that as well. Then we have made sure that not just hypothesis testing, but also parameter estimation can be done with intuitive, meaningful parameters and differences between parameters, namely the treatment effect in the population as a whole, the average treatment effect. And then finally, we do take into account that there may well be excess zeros. Good. That's a long list of features. Everything in blue I just mentioned. There are a few things in non-boldface black. Like we can switch the way we estimate our parameters from likelihood to base. There can be under dispersion rather than over dispersion, etc. So we can go a little further, but it's time to reflect on where does that leave us? All that, let's say, elaborate machinery, when the data are either coming from a relatively small study and or when we have a lot of repeated measures over time. So, and we have a lot of time points. Think again of the example of wearable devices where we have huge amounts of data. We need to think about that because a model of the type presented here may simply break down computationally. It may not converge. It may give more error messages rather than parameter estimates and hypothesis testing results. or in the best case, it may take forever. So we need to think about that. Okay, what I've discussed is summarized here in these references, and it's now time to address the question that I've put on the table. For that, I would like to reflect with you for a moment on one of the most common paradigms, maximum likelihood estimation. Well, I will not go into too much technical detail, but just imagine that for a number of subjects, and say, I record once for a given week their total number of epileptic seizures. Okay, and I relate that to covariates, age, gender, the treatment they were given, etc. So let's say I choose a Poisson model or a negative binomial model. I choose my model. I know what outcome I have. I know what covariates I have. Only the model will contain parameters, regression parameters, or variance parameters, etc. So parameters. So everything is known except for these parameters. These need to be estimated. If they would be known, we could stop here, of course, but the problem is to estimate these parameters, base hypothesis testing on them, estimate the size of treatment effects, etc. Good. So what is the likelihood, or actually the log likelihood as we usually write it down? It indicates for every possible value of my vector of parameters, how likely it is. So I can say I have for a single parameter the theta axis, and I have the log likelihood. Often, if all goes well in simple settings, I would have a function of this form where there is a certain maximum. And what do we know about the maximum? Well, there's a maximum likelihood estimator. Huh? And at that point, if I draw the tangent line, it's a horizontal. If I draw the tangent line here, and if you have forgotten what the tangent line is, I'm just showing it here, is the line that actually sticks to the mountain. If you're skiing down the mountain, your skis will actually be the tangent to the mountain, unless you break them, and I hope not. So the tangent line at the top is horizontal. A different way of saying that is the first derivative is equal to 0. So that's what we have to solve for. We solve a system of equations, and the second derivative is used to estimate precision, standard errors. Okay, the general theory of likelihood is pretty much in these two slides. There is a lot to say. People have written books about it, but that's the essence. The only thing is writing down the likelihoods, the log likelihood, taking first derivatives, and solving that system of equations. That's in many cases much easier said than done. So what are we going to do then? We may simply be faced with situations where there is no solution. Pardon me, no closed form solution, which means I cannot write down theta is equal to and then a mathematical expression. No, I need to resort to numerical techniques. You start with a guess, we call that starting values, and then you iterate until convergence. But an iterative process, when you have a lot of data, may be extremely slow. And when you don't have a lot of data, small number of patients, for example, in the context of a rare diseases study, you may have very unstable iterations. Rather than finding the top of your mountain, you may shoot off in outer space and never find the maximum likelihood estimator. So that needs to be improved. There are many ways of doing that, but one thing I would like to put forward here is pseudo likelihood. Pseudo likelihood means actually something close to likelihood, but not exactly likelihood. So just to fix ideas in a very simple setting, suppose we have a large number of measurements per subject, but I'm going to write it down for 3 only because I can make my point already with 3, but think of hundreds of thousands or so. Well, a likelihood for a long vector will be extremely complex, heavy, difficult to move, slow. So we replace that, for example, by all what we call conditionals. Yeah, and if I have 3 measurements, there are 3 conditionals of this type. If I have 1,000, there are 1,000. That's still a large number, but each of those is very easy to manipulate. So I break it up into something else that increases in size, but that remains much more manageable. That doesn't explode exponentially in terms of computation, but just linearly. Sometimes we look at pairs. If I have 3 measurements, there are 3 pairs. If I have 10 measurements, there are 10 times 9 divided by 2, 45 pairs. But the thing is, yeah, there are 45, but pairs are manageable. 10 measurements at the same time may, in some cases, not be so manageable. So essentially, what I do is I replace my function, which should be of length 3, or in general length 100 or so, by a set of functions that are simpler, no longer the likelihood. So maximizing that function is not maximizing the likelihood, but here's the thing. It doesn't maximize the likelihood, but it still finds an estimator that is valid. Something equal to the maximum likelihood estimator, or more realistically, something that is close to the maximum likelihood estimator. In other words, I solved the wrong problem, but I still get the right answer. Is there no price to pay? Yes, there is a price to pay. I have a consistent estimator. Check, that's good. I have an asymptotically normal estimator. Check, that's good. But the efficiency, that means the standard errors, may suffer a little bit. The standard errors may become a little larger, but a little bit is an important qualification here. In many examples, the loss of efficiency will be such a minor price to pay if you turn a problem from hours in minutes in seconds, or you turn a problem from infeasible to feasible. That's an infinite gain in, of course, computational power, if you wish, or convenience. Good. I'll give a few examples. This is the first example is from a hearing study, an ORL study. The ear is a complex organ, so to study it, we need more than one variable. There we go. 22 variables are followed repeatedly over time in this example. Per ear, we happen to have 2, so that means 44 sequences that we follow over time. What we see here in this data matrix is not a data set, no. It's a data set, but for one particular subject. And if the NI, the number of measurements that we take per subject, is large, we're going to have quite a few of those. So what we now do is say, okay, wait a minute. It's too big to write a likelihood as a whole. I will write a likelihood for the first and the second measurement. And even if the number of measurements is relatively large, I can deal with 2 sequences. I cannot deal with 44 sequences. I'm not going to leave it at that, because if I'm done with 1 and 2, I'll do 1 and 3, ... until I have 144. And then I go to 2, 3, ... until I've done 43, 44. How many pairs do I have? Well, that's going to be 44 times 43 divided by 2. That's a large number of sequences, but just imagine that it's impossible to do for the 44 sequences at the same time. For every pair, it's feasible, and now comes the thing. I have a large number of computer cores, which I can run in parallel. I can parallelize the problem. In that sense, the computation time may reduce to that of just 2 sequences. Yeah, I run that a good number of times, but all in parallel. And then there is just a little bit of post-processing, because all these results have to nicely and tidily combined in a single conclusion. But that is just a bit of post-manipulation, post-processing that won't take too much time. So what we know is that we get valid conclusions and that the loss of efficiency is really very minor. That's one technique. Another technique is based on taking a pair of scissors. Just imagine that I have a data set with 20, 30 subjects, but they're measured a very large number of times. So I have a rare disease, and I have 20 subjects that are followed for years in a row, a register. I have another example. I follow patients, a small number, but with a wearable device, and I get every minute or every few seconds, I get a reading. We have that a lot in cardiovascular studies, for example. Okay, then I need to do something about it because this really large number of measurements may make it completely impossible. There are other settings where I have large numbers of subjects. Let's imagine that in a post-marketing study on a vaccine, for example, I have hundreds, thousands, if not millions of pieces of information. What I then do is I take a pair of scissors. Let's say I have 1,000,000 subjects. I will cut it into 10 pieces. That's 100,000. Still too many. Okay, 100. 10,000 per batch. I analyze all of these batches separately, and then I combine the results of these 100 analyses properly into a single analysis. I've done that now several times. You break up the problem in subproblems, you analyze them separately, and you bring it together again. That requires combination rules, and these combination rules are a bit different between all of the applications that I've been discussing, but similar in spirit. Okay, back to the small number of subjects, but measured a large number of times. I'm not going to split the 20 in 10 times 2, of course. That would be ridiculous. What I will do rather is I may say, okay, let's just imagine I follow these people for 30 days with a wearable device, but I'm going to split the data into 30 data sets each time relating to 1 day. Okay, then I do the same thing. I analyze every day separately, all subjects now, but every day separately, and I stitch that together again. Okay, is this statistically a good thing to do? Numerically it is. It's clear that this improves the numerical stability and speed. Well, for some simple problems like a univariate normal, regression setting, tossing a coin, etc., for these problems, it doesn't make a difference whether I cut and stitch them together again, or I leave them as is. That doesn't make a difference. For some problems, and a good way to think about it is when I have the repeated measures over time, a small number of subjects, but that are measured enormously long over time. In that case, I lose a little bit of efficiency, but that efficiency loss is usually mild. Okay. There is another situation that's coming around the table, and that has to do with, and I will refer to that in a moment again, surrogate marker evaluation, meta-analysis, multi-country studies, etc., multi-center studies, multi-investigator studies, and so forth. So I can also have repeated measures as such a large data set. Some people have 20 measurements, some have, let's say I plan 20 measurements. Some have 20, some have 19, some have 18, some have 17, etc. And if I try to fit my model, it doesn't converge, it diverges, it produces error messages, etc. You know the routine. One trick is I analyze first a group of people that has the same cluster size, the maximal one, 20. When that's done, I have the results, and I start the exercise again for those with 19 measurements. And you get the idea, until I've analyzed everybody in this way. It's not very different from what I did here, but before I just split the data set, think again 1,000,000 people, I split it into 100 data sets of 10,000, not because they had different sample sizes, different cluster sizes, but just because I had too much data to begin with. Here, that may still play a role, but the thing is that the analysis over a data set where everybody has exactly the same number of measurements is much more efficient, much more stable, and in some cases allows closed forms. Okay, but now I have my 20 analyses, and I was talking about combination rules. Yeah, now also the combination rules have to apply. Just to give you an idea that this is not entirely trivial, I can say, okay, I have in this case 1, 2, 3, 4, 5 subgroups. I take the 5 analyses, and then I take the average of those. But wait a minute. Just imagine that the first group is, let's say we have 100 patients. The first group is 80 patients. The next group is 10. Then we have 2, 3, and 5. Yeah, it's clear that the group with 2 patients and the group with 80 patients should not receive exactly the same weight, of course. I can do that then proportionally to the number of people in a cluster, in a group. Yeah, but the 80 people, they have 20 measurements. The 5 people at the bottom, a much smaller group, and they have a much smaller number of measurements on top of that. So maybe I should take not only the number of people in a group into account, but also how many people I have, how many measurements, sorry, I have in such a group. Okay, so I need to take that into account in my average, which will become a weighted average then. But that can be done, and that has been studied and works relatively well. The setting I just described can be made explicit for the case of a surrogate marker. What is a surrogate marker or a surrogate endpoint? Well, that is one which I would use instead of what we call the true clinical endpoint. Let me give you 2 cancer examples. The true endpoint, T, is overall survival. A surrogate, let's say it's advanced cancer, advanced colorectal cancer, for example. S may then be the surrogate, progression-free survival, or it may be tumor growth or something like that. In, for example, neurodegenerative diseases, the true endpoint may be a cognitive scale. The surrogate endpoint may be, for example, a biological measurement like amyloid plaques or tau PET or something like that. When is a surrogate a good surrogate? There are actually 2 things that I'm interested in. One is my surrogate should predict what is happening to me in the long run, for example. So my tumor response, will that be predictive for my overall survival in a while from now? But also the trialist, the regulator, the company doing the study, they may be interested in, okay, the treatment effect, when assessed on the surrogate, is that predictive for the treatment effect when assessed on the true endpoint? And because of the latter thing, because of the so-called trial level surrogacy, again, what is the prediction? What is the predictive power, as it were, of the treatment effect on the surrogate versus the treatment effect on the true endpoint? For that, I need replication, multiple trials, multiple centers, multiple investigators, etc. So I stands for that unit of replication, let's say center, and J is the patient within a trial. Of course, as I was just illustrating a moment ago in this setting, in such a real-life setting, forget it that every trial, every center is going to be equally large in terms of number of patients. Forget it that all investigators are going to treat exactly the same number of patients. So that same problem occurs now. And there are 2 solutions. One solution is I will make the trials or the centers equally large, even though they are not. Let's say the smallest trial size is 5, the largest trial size is 50. Okay, all of them will become of size 50. And how do I do that? I use multiple imputation. Multiple imputation is a way to generate values, predictive values for missing data. And there are no missing data here, but you see what the point is. If I let's say, would multiply my 5 patients 10 times to 50 patients, that trial is the same as the largest trial. By doing it a number of times, not just once, I make sure that I don't start to treat these 45 extra patients as real data points, because they are not. I need to take that into account. It's a bit more elaborate, and of the 2 solutions, it's not the best. The second one is say, okay, for a number of models, if we would analyze the data of a single trial, we have a simple routine, a stable routine, estimation routine, And sometimes it's even in closed form. Now that's blue sky because it means I don't need an iterative process. An iterative process comes with two warning bells. It can take time and it can diverge. It can go to a wrong place, shoot off in outer space. So therefore, I could analyze every trial separately. And then again, yes, guess what? What will we do at the end of the study? We combine the results of these certain number of trials that are analyzed separately into a single analysis. We call that a two-stage approach. But the combination rules can be chosen to make that very efficient, so stable and fast also in this way. Okay, and that's part of the work that we have done on surrogacy, and this is a book that came out in 2017 on the topic. So, as I said, it can, in some cases in simulations, be 10 times to 100 times faster and very efficient, and that can make a difference between feasible and not feasible. I'll give a concrete example here. We have roughly 2,000 patients treated by roughly 200 psychiatrists, but as I said, they're not going to treat the same number of patients, all of them. It ranges from 6 to 52. We have three outcomes, PANSS, BPRS, and CGI. All three are treated as continuous. None of the three are actually. PANSS and BPRS have a large number of possible values, so they're quasi-continuous. CGI, clinician's global impression, or clinical global impression, is measured on a 1 to 7 scale, ordinal, but we approximate that for now as continuous. Okay, what matters for us now is to see whether my simplified approach, trial by trial, I analyze all my trials, so all my psychiatrists in this case, their data are analyzed separately and then weighted. What you see is that if you compare that to full likelihood, REML is actually a form of full likelihood, the standard errors with full likelihood are better than in the new approach. But the new approach, of course, is much faster. That's the point I would like to make. And is there a price to pay? I think we cannot deny. The answer is yes, there is a price to pay. But if that makes a difference in larger problems between a long computation time and a short computation time, we may be willing to pay that price, especially if it makes a difference between infeasible and feasible. Okay. Let me give you one other example of the same. This is an observational study, the Leuven diabetes study. It's a general practice study, 2,500 patients, and we have three outcomes: LDL cholesterol, hemoglobin, and systolic blood pressure. So we have three ordinal targets on a 4-point scale each. And ordinal, that means, it's not continuous, so usually the models become a bit more difficult. And there are three, and they're measured repeatedly over time. So we have three sequences measured repeatedly over time. All right, so we need to do joint modeling for that. That's a summary of the targets that we have available here with their 4 categories. And now we're going to bring something new on the table. That is, why don't we combine a few of the techniques that we have seen before? The baseline is pure maximum likelihood. We have a likelihood that takes into account, that swallows at once the fact that we have 3 sequences that are measured repeatedly for a certain number of measurement occasions. The next thing is to say, okay, 3 sequences, we can actually do the pairwise likelihood, where the 3 sequences are replaced by the 3 possible pairs of 2 sequences. And you see the computation time is going down already. Or we can go from the full approach to the split sampling approach, where we split the data set into 10 or more pieces, not just 3 pieces, more pieces are possible, of course. And the computation time goes down. And then, of course, we can do the 2 at the same time. Pairwise modeling every time on a subset of the data set. And that means that the effect of the 2 simplifications is superimposed, and we really reduce the computation time. Now, maybe you're thinking, well, 7 minutes, it's not the end of the world. No, if you're fitting a single model, I agree. You can start up your program, go for a coffee or a tea. When you come back, the result will be there. But if you're doing modeling, you say, okay, I will construct a likelihood model, and then I'll see, do I need age? Do I need age squared? Do I need gender? Do I need the age by gender interaction? All different models. I'm building a model, I'm doing backward selection, forward selection, whatever. Yeah, every time 7 minutes or a bit more, that is adding up. And I may be busy for a few hours, for example, whereas if I combine these two approaches and every calculation takes 20 seconds, well, I can just keep doing it. It's just one single simple exercise. It's all nice and well, but if this now would come with a drastic reduction in precision, I would not be so happy. Then I would prefer to do the 7-minute thing. But if you compare the standard errors in the gold standard, which is maximum likelihood but slow, with the pairwise likelihood, which is cutting corners in two ways, but still with valid estimates, I see that the standard errors, it doesn't make too much of a difference. It's about the same order of magnitude, occasionally a little larger and sometimes even a bit smaller. So there's virtually no price to pay. Still, the 7 minutes to 20 seconds, it's clear that is 20 times faster, but it will still be doable with the 7 minutes, right? Well, these models, as I said, they're for ordinal data, not for continuous data. That means internally in the internally in the numerical optimization, I need to calculate a bunch of numerical integrations. And that also takes time. And a numerical integration is basically, if I need to integrate a function numerically, what I do is I replace it by rectangles locally. I calculate the surface of these rectangles, and that's a good approximation. The more rectangles, the better. So if I go from 3 to 15, it's more precise, but yeah, it takes also more time. Look at that. The 7 minutes have now become 10 hours. It's more than a working day. It's a night in between two working days. But the two devices that I've used, think again of what it was, pairwise modeling on the one hand and splitting the sample, brings it down to 4 minutes. Okay, that's a bit more than the 20 seconds, but I can do my analysis still in a few hours, say, whereas if it's 10 hours and I need to fit 5, 6 different models every time, it would be running for 10 hours. I'm not going to get it finished in a week unless I'm going to lose a lot of sleep. So this is a device that already may be useful even when I have a small number of subjects, but these subjects have a lot of measurements repeatedly over time. Do I lose a lot of precision? I don't think so from what I saw a moment ago. Not only that, also in the case where I have a more refined integration, it's still very good efficiency, 90% or more, so to speak. So to round off, let me repeat what this was all about. We often have complex data in rare diseases and beyond. We may have relatively small number of subjects, but they may come from various countries, various centers, various investigators. The subjects may be followed repeatedly over time for a very long time. They may be measured for not just one thing, but for many things at the same time. And ideally, all of that would have to be modeled at the same time. Well, classical likelihood or Bayesian inference, forget about it. But if we want to keep interpretability and meaningfulness to our models, we still would like to do something like that. So pseudo likelihood, splitting the sample, doing an analysis by cluster size, doing an analysis by investigator, etc., and then later bringing it together offers great advantages. It makes something that otherwise is not computable suddenly much more feasible. So the advantages of what I have proposed are twofold: time reduction on the one hand, and at the same time keep it feasible, but also stability of computations. Recall that some of the techniques allow closed forms. closed forms cannot diverge, and especially for small sample sizes, that may be a very important asset. All of this would be to no avail if we have to pay an enormous price in terms of precision, but that's not the case. So I think in the context of rare diseases, techniques like this, and they were illustrated in a number of settings here, but they can be applied to many more, offer a very viable vehicle for data analysis. Of course, next to many others, randomization-based semi-parametric methods, etc., that people are also using and that are discussed elsewhere in the webinar series. And with that, I would like to conclude here.